Hello, good morning to all of you.
Good
Good
morning,
morning,
sir.
sir.
Good morning, sir.
Good morning, sir.
Good morning, sir.
Okay, so in previous class, we have started from configuration, transistor BJT configuration, and in that I told three configurations are there: common base, common emitter, and common collector configuration. So this word is common base means base is common to both input and output. For example, here it is common to both emitter and collector end. Similarly, if you're going for common emitter, emitter would be common, and in common collector, collector would be common. So now if you see the configuration, now we have to see the features or characteristic of this configuration. So if you're going for a characteristic, then we have to plot the voltage and current behavior uh, of this configuration. So now if you see this voltage and current characteristic, so you'll get two characteristic here. One is input characteristic and other one is output characteristic. So input characteristic, if you see, so you have to see the behavior of current IE and what is the supply voltage you have given. Similarly in output also, what is your supply voltage and what is your output current. So based upon that, it is discussed as input and output characteristics. Now, if you're going for input characteristic, now this plot you have to do in between. Now, what is input voltage here? So it is your VEE. And what is the current if you see? So what is the current IE? Now this behavior if you plot, now if I'm plotting at a constant, because this is also your supplying supply voltage VCC. So a particular supply voltage if you plot or you are varying this input voltage. So now you have to, for different input voltage, the behavior would be look like this. So emitter current will be controlled or flown based upon what input voltage you are giving. So this V also you can term as VB because this is the voltage between base and emitter. Also we can name is VB. So if you are taking a silicon transistor, now you can see this after this, because if you see this I'm supplying input voltage and already I told this is should be forward biased. So you can see it is a act as a p-n junction diode and you are supplying your voltage. Now it will show or it will behave like diode characteristic. So after this potential barrier of this junction, so then current will be flown. So if you see for this is silicon based transistor, so then this will be your 0.7 volt. If I am taking germanium, then it will be 0.3 volt. So this graph you are plotting for at a constant output voltage, that is VCC. This can be also VCC or you can say VCE because this is voltage in between collector and emitter. So that's why this input characteristic you can see this practical if you see. So this is your input characteristic. So I have done some mistake here. VC, not this is collector and base. So this is not VC, VCB. So this is the voltage among collector and base. So if you're plotting a different VCB values or VCB or I can say VCC also, same thing. The naming depending upon the potential difference between two terminals. So accordingly a different collector base voltage. If you are plotting the voltage VE or VB versus emitter current, so this is the behavior and this is the input characteristic of your common base configuration. Similarly, if you go for output characteristic, so if you go see the diagram, output characteristic will be IC versus VCC at what input you are giving, because at what input you are giving, based upon that your output will vary. So here if you see input will be this is a current control device, so based upon your input current, so input current will be IB. At different IB, what is the IE versus VC, that is the output characteristic. So here you can see IC versus VC B or VCC you can take. So then a different IB, these are different IB values. So different IB values you can plot. So here you can see this is IB, all IB values are given. Am I audible to everyone? Hello?
Yes,
Yes,
sir.
sir.
Audible.
Yes,
Yes,
sir.
you're audible.
So then why you are not telling? Because output current is here. What is the current here? IC, na? So this current versus what is the supply voltage you are giving. So this is your IC. So a different, this plot you are giving between IC and VCC. IC and VCC, and depending upon what input current you are giving. So here what is the input current? Anyone can tell me?
IB.
IB or IE? What is your input characteristic? Input characteristic is in between IE versus VE. So what input you are giving, what I told, output characteristic will depend upon input only. So what input you are giving here?
IE.
Ah,
IE.
ah. So because you are only listening whatever I'm saying, also you use your logic. Na? I have shown the diagram. So input characteristic you are plotting. Why? Because you are observing how IE is you are getting based upon your supply voltage VE, input supply voltage VE. So now I will change. Now this IE will given to your this network, and output will depend upon your input current only. Now input current is IE. So here for common base configuration, this IE will be input and IC is the output. If you will take common emitter configuration, then IB will be input. That we'll see in the diagram. First you understand this diagram very clearly. This diagram you should understand, then everything you can do. And if you want to here, I will make it once again. So this diagram, now I'm taking symbolic point. This diagram I'm doing. Now I'm biasing here. Same thing. Now your emitter base should be forward biased. So if it is forward biased, so then I have to connect, because this is, you can see this is NPN transistor, because NPN transistor. Now here it is forward biased, means it should be like this. This is plus and this is minus, and this is forward biased. Now if you are going for, this is your reverse bias, so here I have to connect here, this is reverse biased. Now based upon that you can see what is the, if I'm taking, I can write this is VBE or I can write VEE. Here also I can write VCB or VCC or VEE. Okay, so now this is your input loop. Input loop. So the feature based upon this input voltage, so what input current will change. So that's why IE versus VE at different VCB values. Similarly, when you go for output, so output is IC current What is your supply voltage? VCB at different input current. So this behavior will be like this. So a different IE, this feature will be there. And this is your output characteristic. This is input characteristic, and this is your output characteristic. So different IE values I can plot. So this will be like this. So that's why that graph is shown. So that is this graph is shown. And here I have written this one IB, but this is your IE at different IE values. So different IE values, this will be okay. Now this is example is this is a practical case given for common the silicon based transistor. This is the output characteristic at different IE values they have plotted. Now already one thing I told, because we have taken input loop is forward biased and output loop will be reverse biased. So if you are taking this biasing, then you can see this unshaded region, this region you can see this is known as active region. So this active region you are obtaining when you are doing input is forward biasing and output loop you are doing reverse biasing. So now coming to your mind that biasing can be both can be reverse biasing and both can be forward biasing. So here you can see if both you are doing forward biasing, so then this region will be there, saturation region will come up. If I am doing input and output loop reverse bias region, so then it will be in cutoff region. But why we are going for active region? Because you can see this behavior output. You can see your whatever output current IC is constant over this region. So then you can see this amplification. If you are going for output current by input current, so you are getting a constant factor. So that's why this region is used for amplification case. But common base is used as an amplifier, not it is a very high gain amplifier compared to common emitter, but still your amplification factor you can see here you will get in this behavior. Okay, so in this slide any queries till now, any queries anybody have, you can ask. So in this diagram you can see 6 variables are there. One is input current, output current, what is input voltage and output voltage. And these are the 4 variables, and using that you are plotting input and output characteristics. Is it clear or any clarification is required? Hello?
Sir, why saturation region is drawn? What is the need here?
No, because you can see biasing is required because to flow the current in the device. Now to flow the current, overcome that you are supplying the voltage. So biasing you are doing. Now whenever you are doing biasing, now forward biasing I can do and reverse biasing I can do. So then you can see one can be forward biased, other can be reverse biased, or both will be forward biased or both will be reverse biased. So these 3 combinations are coming, or you can take also reverse bias and forward bias. But if you are taking input loop reverse bias, then there will be no flow of current because only minority carriers will be available. So that's why these 3 configurations are there. Now forward bias, reverse bias, or your forward bias and reverse bias. So if I'm taking this configuration and if I'm plotting the behavior of voltage and current, so this behavior, this graph you're obtaining. Now why this region is active region? Now in active region you can see this amplification, or this you are getting a constant output over this range. So then this range or this region is known as active region. because here you can device you can use for amplification purpose. But here you can see in saturation region, if you are doing this, so you can see this behavior, and this is obtained at when we are obtaining, when you are taking, this is your you can see how much voltage you will give, and in this region, this current, you can see there is a sharp increase, depending, if you see there is sharp, this behavior is there. But in amplification, you need a constant amplification. So this region, because this behavior obtaining, but this behavior you cannot use for amplification purpose, because amplification you should got a constant amplification over the range. Now this is, you can see other region which is coming in cutoff region. So here you can see if you're going, this device will be cutoff region, and this region below this you can see IE is equal to 0 milliampere. So which is not required. And when you will get, when I am taking cutoff region, because this behavior we cannot use for amplification purpose.
Sir, what will happen if we means reverse bias the input loop and forward bias the output loop?
Which one?
Means what will happen if that input loop we are forward biasing, if we reverse bias it
Here,
and
here you are telling.
yes sir, if we
This
reverse
graph,
bias this one and forward bias
this
the
is,
output loop, then
yeah,
what will happen?
reverse bias, this is forward bias. Okay, so already I told reverse bias condition I told, because there is no IE will be 0. So there will be, because if you see reverse bias I am doing, so this reverse bias is there. So now this depletion region will be more, na? So only you can see only leakage current or minority current will be there. So which is also very, IE is equal to 0. So this
This is the case when the input loop is reverse bias, right? And
yes.
the other loop is also reverse bias.
Other
Reverse
loop
bias.
is forward bias, means if we forward bias the output loop and the input loop is reverse bias, then what will output we will get?
What you told once again?
If the input loop we are reverse biasing and the output loop
Okay,
we are
reverse biasing.
forward biasing. Our
Forward
output,
biasing.
yes sir. Output
biasing.
we are forward biasing, then what will be the means characteristic of the graph?
For both are forward biasing, you are telling, na?
No sir, one is reverse biased. The input is reverse biased and the output is forward biased.
That's why I told, and this reverse bias is there means you can see depletion region will be more, na? So only minority carriers will be there. So leakage current only will be there. So majority current will be 0 only, na? So it is similar to your reverse bias condition.
Okay.
Because you can see in input biasing, why you're doing this, because your majority carrier should flow and current should be maximum, and whatever current will exist due to majority carriers. And if you're doing forward biasing, and depletion region will be reduced. So that is the logic you are using. You can, because I'm not telling it is not possible. In research, every configuration, every biasing you can give. But what output you will achieve, and based upon that output, what operation you can do, that is very important. Okay?
Yes sir.
So if you are taking both forward bias and reverse bias, or you can see better use we are doing in reactive region. And why we are doing reactive region, you can see based upon your IE, IC also vary. So now you can see particular IE, I am getting IC value is this much, and which is constant over this one. So this reactive region, if you see transistor to operate as efficient use, so we are using in active region. And most importantly, we are using in, for amplifier case, you are taking active region. And these regions are also there. Some dedicated applications are there also, which is not, which is very, you can see a particular application whenever you require this type of behavior, where IE should be, you can see here IE, you can see the IC is linearly increasing for a particular IE value. For that type of application, when you need a device where there is a very sharp change in current, that particular application you can use your transistor should be in saturation region. Are you getting me? Hello?
Yes sir.
So this is what I'm, once again I'm repeating, this is the behavior of your common base transistor when you are doing biasing, either you can take any combination, and if you're plotting the behavior, you will get this type of feature. So in also lab, one experiment you will do, not common base configuration, common emitter configuration. You have to plot the behavior of this graph, and also you can see, because there you are getting this type of behavior. If you are plotting at a constant IV, there we'll see. So you will feature, or you have to draw the transfer characteristic, or you have to draw the output characteristic of a transistor. So this behavior, this similar behavior will get it there. So also you can experiment or simulation point of view. Also you can see different vary the phase accordingly, and you will see the current behavior. So same thing also I have highlighted here. So in active region, collector base should be reverse biased, while base emitter will be forward biased. So base emitter is input loop, and this is your output loop. For cutoff region, you can see both will be reverse biased, and for saturation region, both will be forward biased. So the whatever behavior it is plotted there, these three regions it is already shown you. Now here one factor is there that already I told BJT or FET are characterized by the amplification factor. Like in a transistor, you have seen I told beta value, or in FET I told transconductance. So here that beta value, why I told beta is similar to your alpha amplification factor, because in either three configuration you have seen, common emitter configuration we are popularly used. So in common emitter, that amplification factor is known as beta. In common base configuration, we are telling as alpha. And in common collector configuration, we are discussing as gamma. But all are amplification factor. So there, if you, in the first slide, you can change there. Either you can write alpha or beta or gamma based upon the transistor configuration. Now here alpha is for common base configuration. So what is the, you can see if a transistor is op mode or AC mode. So if you are taking in DC mode, so what is your output current divided by input current? So amplification factor means, if you see what I told, amplification factor. So what is your output current? Output current is IC. And what is your input current? It is your IE. Okay, so this amplification factor, output current by input current. Okay, so if you are taking for this common base configuration, I can take this is alpha. Simple meaning. Okay, and if you have seen in transistor, what relation I told, IE is equal to IB plus IC. And IB is very smaller one. So then that's why you can see, or IE is greater than your IC. So you can see this value should be less than 1. Are you getting me? So this value will be less than 1. So here, if you see to the design efficient one, so practical values for this configuration, amplification factor is equal to 0.998, because IB is less than, IB is also present, and IB value is very small, so that's why. So we can write alpha IC by IE. The practical device, this is in between 0.90 to 998. Are you getting why these values are 0.90 to 998? Because IB is also present there, no? And IC is less than your IE. And also you can see your IC is combination of IC majority and IC minority. So here also you can write IC is equal to alpha I plus what is the current due to minority carriers. So this expression also you can remember, which you can use later on also, simple thing.
Sir, why is it called amplifier? It is not amplifying.
No, that's why it is not a very, you cannot say it is a very good amplifier, but sometimes it is used as amplifier also.
Okay, sir.
So that's why you can see common emitter is popularly used, and that beta term, they are also output by input. That is also we are using. So this, you can see this amplifier we are using for high frequency amplifiers, because in high frequency, because this amplification also required, so that this type of common base configurations are used there. So for AC, similarly for AC mode, same thing, change in IC by change in IE. So whenever the this is your alpha or amplification factor. Any queries in this? Any till now? Anybody have any queries?
Sir, what is ICBO?
Your voice. Tell me once again.
ICBO.
This is already you have seen when I have explained the transistor or transistor property. Total IC is equal to IC majority because due to forward bias, and this is due to the reverse bias because two layers are there. No? If you remember, two layers are there. This is thinner and this is thicker. And during forward bias, you can see the current whatever is flowing due to IC majority. And here due to reverse bias condition, whatever current is flowing, this is I minority. So total will be, because output current is IC, so total current will be due to majority and minority. So this IC majority plus IC minority. And when I'm writing in terms of alpha thing, because alpha you can see IC by IE. So whatever IC you are writing, this current is due to majority carriers. So whenever you are finding out by output by input, so this alpha you are calculating, this is, if you see, this is IC majority actually. Okay. So due to that, we are putting this relation between IC majority and IC minority. And why it is written you can see it is when CB means when common base open. So that's why it is written like this. And this is due to minority carriers you are getting.
Okay, sir.
Okay, so this is you see. So this alpha also is known as amplification factor, or you can say common base short circuit or common base short circuit amplification factor. So what is common base configuration? And you can see amplification factor you are getting due to this, what is output by input, that's what is given.
Sir, in the last slide, you wrote IE equals to IB plus IC. In that case, was it for majority carriers or in total?
This is in total actually, because IE is equal to IB plus IC we are writing. Because if you are going for IC, total IC is equal to IC majority plus IC minority will be there. But this is because if you see IC minority or what is the minority current, it will be negligible actually. Very minimum, you can neglect it. Here this part, if you when you are doing mathematically or circuit analysis, you will do at that time you can neglect. Okay.
Sir, is the minority current because of IB?
Once again, repeat.
Is IB's current, is it related to ICO minority?
No. IB is different and ICB0 is different. ICB0 you are getting due to this depletion region, okay? And IB is always there. IB is, this one is IB.
Okay.
Okay, ICB0 and ICB are different. If you see in magnitude point of view, IB is in microampere, okay, And now this leakage current, you can see for an ideal device, it should be very in nanoampere. But already it is temperature dependent. When this device is used in different temperature level also, that sometime that current may be some increase to microampere level also. Okay. Already you have seen now, because when I started in diode, in reverse saturation current we have discussed, and how reverse saturation current is controlled. That is same thing in this leakage ICB0. So ICB0 is reverse saturation current. You can see similar. It is same to that only. Okay, clear it? It is clear?
Yes, sir. Thank you.
Okay. Now one simple example, you can see how transistor is amplifying. If I'm taking common base configuration, here you can see if I'm giving 200 millivolt input signal and input R1 is 20 ohm, and your output impedance is 100 kilo ohm, and your load resistance is 5 kilo ohm, and what is the how much amplification is there? Can you calculate? So what will be the amplification, or what is the output voltage you will get it? Can you calculate what is the VL? Anyone can do this? Simple. What happened? Anyone? So first you find out what is the input current, and input current and output current are same, no? Because IL and IE are same. You have seen in common base configuration. Now once you got IL, then you can find out the voltage VL, IL into R.
35.
How much? 35.
सर अल्फा को मल्टीप्लाई करने के बाद
Here alpha is already 1, na? So I1 is equal to IL, because that's why it is given.
हाँ yes sir.
So because you are using a transistor here, na? Because to find out the voltage, you have to find out the current, and this current is equal to your input current, because here alpha is approximately 1, na? Common base configuration. So alpha IL is equal to IE. So IE, how to find out? Now voltage is given and resistance is given. Okay, you see, simple thing. So what is input current? Right. So which is 10 milliampere, and 10 milliampere is equal to your because I1 II is equal to IE is equal to IL. So 10 milliampere. Now what is the voltage now here? So IL into R. So 50 volt. So what is the voltage again? You are getting approximate 250 times. Now what other important information you got? Now you have seen current gain is equal to 1, but voltage gain will be more. So common base transistor configuration, you can see where you may get current gain is equal to 1, but voltage can be amplified. Is it clear? Hello?
So here the output voltage is 100 kilo ohm or 5 kilo ohm?
5 kilo ohm, because you are measuring your output voltage across RL only. Because this is your Z0 output impedance if I'm looking to this one. But I have to calculate or measure the voltage across the load resistor. So this current you have to find out across load only, because when you are measuring across the load only, na?
Sir, then what is that arrow?
So that is common. Now you will start next because if I'm taking a two-port network, so you will see read it network theory next time. Now if you see this is your two-port network. Inside this network can be anything. For example, now whatever input voltage you are giving, okay. So for example, I'm giving some voltage here, VI. So here voltage you are giving. So current is flowing here. Now some reflection also be there in this port, and some current will flow into this. Similarly, if I'm taking output voltage here, now current will flow here. This is I0. This is II. Okay. Now here in this two-port network, you can see what is happening. Now if I'm measuring the impedance of this network, so this is known as Zi. And if I'm measuring this impedance, that is Z0. So I will also tell you in transistor, when you do the equivalent circuit of transistor, this is the impedance of this box, this two-port network, or you can take as a transistor or any device. So this transistor impedance, output impedance is Z0. But what is the load you are taking? This is your load resistance. Across that you are measuring your voltage. Okay, Z0 is the impedance, or I will tell you, okay, here this Z0 how to calculate. You have seen this previous diagram also, which you will calculate here. Now here output impedance, how to calculate? Output resistance or impedance, how to calculate? Change in voltage by change in current. So change in voltage means this is your VCC you are giving. For example, I am taking one change in voltage. For example, this line I am taking. Okay, so I have to take tangential line or two difference point. So here you can see, if I am taking change in VCC divided by change in IC. Okay, so change in VCC will be some value will get. Change in VCC means, for example, I am taking this is the range. So corresponding voltage will be change in VCC, some value will get. Okay, but IC, you can see change in IC is equal to 0. VCC by 0. So here you can see impedance is equal to infinite. So this is your output impedance of your device. Are you getting me? Hello?
Yes, sir.
So that's why you can see this output impedance here in example you have seen. So this is your output impedance, which is a higher value. That graph I have shown you ideal. So practically you can see this output resistance is very much high. And how to calculate that? That you are calculating the transfer characteristic or output characteristic of that device, PNP transistor. So which is a higher value. But we are doing measurement across RL, but for practically it should be same. Or you can see ideally we should take, because impedance matching should be there. But we cannot take that impedance value because this is of your device and this is your across that load you are measuring the voltage. So in this question, your RL is given 5 kilo ohm. So that's why you are calculating the voltage across RL only. To get that voltage, I have to find out how much current is drawn. So current is drawn is equal to 10 milliampere, and then you are calculating the voltage. Clear?
Yes, sir.
See, load voltage you can vary. So that's why load voltage you can take 6 kilo ohm, 10 kilo ohm. It is up to you. But in this question is 5 kilo ohm. That's why finding it out.
Okay, sir.
I hope every part is clear.
Yes, sir.
So typically, if you see, if some company are developing some common base or transistor and you are doing common base configuration, the amplification you can see it is approximately 3 voltage gain you can obtain up to range of 50 to 300. But now devices are developed, this range can be different for different transistors. But generally, you can see it is in between 50 to 300, and current amplification you have already seen, it is nearly equal to 1 or less than 1. Okay, so this is all about common base configuration. Now we are going for common emitter configuration, which is popularly used. So common emitter configuration, you can see diagram. So emitter is common. Now emitter is common. Now you can see I can do symbolic representation also. So common base, this is common emitter. Now here you can do forward biasing. So base, this is you can do forward biasing, and this is you can do reverse biasing. Okay.
Hello, sir.
Tell me.
Sir, if we have to down the voltage, input voltage,
We have to
down,
tell me in any okay. Tell me once again.
we have to make less output voltage than input voltage.
Which case? Previous case you are telling?
Yes, sir.
What you are telling? Once again you repeat. Tell me.
If we have to make less output voltage, then what do we have to do?
So then you have to take the low resistance, 1 kilo ohm.
In which part? In
Now load resistance you can change, na?
okay.
Now if you are taking load resistance less, so your output will be less only, na?
It will be less, but not less than the input voltage.
We cannot take that one, na? Because I have to use the amplifier. Here what I told, voltage can be obtained. Now based upon current gain is 1, because this you can see this behavior of this device, I is equal to IC. So that is current gain you are getting 1, but voltage gain you can achieve more than 1. So now you can see one example we have taken. Now you can see voltage gain we can based upon this resistance value you can take, or you can retrieve more voltage. And how you're doing this? Because this due to this device. Okay, you're telling practically how it is happening. You're telling me that one? Hello?
No, sir. I am telling how to get less voltage than the input given input voltage.
Why? Why you will take less? Already you have higher value. Any device where you need to take the less value of that? Are you getting me? Where you will use the practical application?
If we have a very high voltage in input, then we have to down that voltage to use it.
Then you can use attenuator. Why will take a active device? You can take a passive device. Will dissipate only. So I can use a variable resistance. So will dissipate the energy, and at the output you will get the less voltage. Or you have seen in step down transformer. So why will you use this transistor? Are you getting me?
Okay, sir.
Now that transformer you are using for high voltage, or for your thing also I can say variable resistor you can use. Like in lab also sir has shown you, na? For example, you have 200 millivolt, and I want to take output is less than that, or I have to take 100 millivolt. So then what you can take? You can use a variable resistor. Then your some dissipation will be there. Are you getting me? The circuit will be like, if you're giving, for example, I am giving 200 millivolt. Now what you are telling, I need here, for example, 10 millivolt. So then here I can use a variable resistor here. Are you getting me? So based upon that variable resistor already I have shown you, na? So that
Yes,
also I can use. Then why will you use that transistor here? So transistor, wherever you need some amplification, at that time I have to use active devices. So now here you can see voltage amplification can be done. That's why we are using.
Sir, here if we connect one resistance in series with this RL, then there will be some voltage drop across that resistance also.
This
so then
is not
the voltage across RL will get reduced automatically. In that
that's
way,
no. Then why will you use transistor? Transistor used already. I told this is an active component.
yes, sir.
So if I told designer, or we are the designer, we have to select what component I have to use. Now in your class, what I'm saying, the devices can be used for this, because this is active device. You have to, wherever you need some amplification factor, you have to select this transistor. And this is the logic behind it, how to use the device.
Yes,
now,
sir.
Based upon the application point of view, you have to select the circuits. Now, best designer, who is best designer? who are using minimum components and they are finding they are obtaining what value they want to use. Now for your case, what he asked, so you want to attenuate, so you can use a register, simply register you can use. I
Yes.
hope I clarified his question, or any other thing you're asking.
No, sir, that too.
Now here, if you are going for common emitter configuration, here you can see amplification factor, current amplification factor beta will be higher. That we'll see how it is higher. We'll see it here. Okay, you have any next class is there? Hello.
Yes, sir, maths.
Okay,
maths.
then okay, you can leave it. Next class will discuss.
Sir, about the mid-sem examination and the exam pattern syllabus.
So because in your you can see already 3 branches have same course, so there will be a common question for all the branches, and till 8th, because we are planning to this transistor basic, up to transistor basic question will be there. Okay, once it will be finalized within 1 and 2 days, the pattern will be disclosed in your Google Classroom. Okay.
Okay, sir. Thank you,
But
sir.
don't worry about that part, but question will be asked up to transistor, whatever discussed to 6th or 7th February, up to that it may be asked in your exam. Is it okay, or any other queries? Hello?
Sir, can you share the complete presentation of the semiconductor diode? Because, sir, in the classroom, there are parts and parts, and it becomes very disorganized.
Okay, I'll share it. Okay.
Thank you, sir.
Thank you, sir.
Any other thing?
Thank you, sir.
Okay.
Thank you, sir.